All right, hello everyone, and welcome to our last video of Unit 7 for the AP Chemistry curriculum. Today we are going over solubility equilibria as well as the common ion effect. So in Unit 7.11, we're going to start exploring solubility equilibria, which focuses on how the dissolution of an ionic solid is actually a reversible equilibrium process. We're going to learn how to write and interpret KSP expressions, understand what the solubility product constant represents, and then we're going to use it to calculate the solubility of a salt. So solubility equilibria is the idea that when a solid salt dissolves in water, it doesn't just disappear, it forms a dynamic equilibrium between the solid and its dissolved ions. Now in this example on the right here, we have solid silver iodide put into water, and then you can see that some of the ions, the Ag plus and the I minus, come off of the solid and then dissociate into free moving ions throughout the water. That is what the solubility equilibria is all about. We are measuring how much of the ions are dissociating into the water and how many of them are staying as solid form. So at equilibrium, which kind of we are showing here at the particle level, you can see that some solid silver iodide is still present at the bottom, while some of the Ag plus and I minus ions are dissolved in solution. So that dissolving and recrystallizing, those are happening at the same rate, and that is dynamic equilibrium. So we're going to describe this type of equilibrium using KSP. So it's K for equilibrium constant, just like we've always done, and then SP that stands for solubility product. Now, it's important to note that our reactant here is a solid, and remember we do not use solid or liquids in our equilibrium constants. So when we're doing the expression for KSP, it will only be the constituent ions that are products. So in this case, it'd be Ag plus and I minus, and those are still raised to the power of the coefficient. It's just that in this specific one, we have coefficients of 1. So now that you understand that KSP is a relationship between the amount of ions that are in the water, we can try to figure out what that means in terms of different types of salts. So sodium chloride is a salt that we all know well enough. It is table salt, and when we put that in water, it's really easy to dissolve. Once we mix that up really well, we don't see any solid NaCl in the water anymore. So you can assume that our value of Na plus and Cl minus is going to be really high because we have no solid left over. So when you have a very high KSP, you're going to have a very soluble salt. On the other hand, when you have one that does not dissolve well in water, that means you're going to have a very low KSP because you're not going to make a lot of those constituent ions that are floating around in the water. So like mentioned in the previous slide, a large KSP means that the equilibrium favors the ions over the solid. That means that more product ions are present at equilibrium, so the substance is generally more soluble. That's why something like NaCl dissolves really easily and strongly favors the Na plus and Cl minus in solution, and therefore has a very large KSP value. A small KSP value means the equilibrium favors the solid over the ions. So only a small amount of that solid is going to dissolve as the constituent ions. And so the substance is generally considered insoluble. AgCl, like we've talked about in past units, is a very common precipitate. When I say precipitate, I mean something that does not dissolve in water. It's left over at the end of the reaction. So whenever you see AgCl, just remember it's deemed insoluble, but in an equilibrium reaction, remember, we're still going to have some of those Ag plus and Cl minus ions. They're just going to be negligible in terms of the grand scheme of things. All right, so now what I want you to do is pause the video, and I want you to identify the most soluble salt in this table below here, and then I want you to tell me the most insoluble salt on the table. So let's start out with our most soluble. So remember, most soluble is going to be my larger KSP values because it means it's going to favor the product or the ions. So if it's more soluble, it means I have more ions in solution. So if I'm looking for the largest KSP value, I'm looking for my KSP value with the lowest exponent, which is going to be FeF2. So that is the largest KSP value, which means that is my most soluble. And then looking for my least soluble, I see I have a 10 to the negative 16th. So that is my lowest KSP value, meaning I'm not making much ions. I'm going to have a lot of that salt left over. So this is going to be deemed an insoluble salt and have the lowest KSP out of all of them on the table. All right, so calculating KSP, you need to remember a few things. Number one, do not include the solid reactant in our expression. Remember, any of the equilibrium expressions do not include solids or liquids, and that is no exception for KSP. The other thing is your products are going to be aqueous. They're going to have AQ next to them. That's just symbolizing that they are dissolved in water. And then finally, KSP is going to be constant at constant temperature, just like our other equilibrium expression constants. So looking at this equilibrium that we're given, BaSO4 or barium sulfate, is going to be put in water and it's going to be able to dissolve into its constituent ions, which are Ba2 plus and SO4 2 minus. The question says to write the KSP expression for this solubility equilibrium. So it's going to be very similar to the others, except we are not going to have any reactants in the denominator because the only reactant we have is a solid. So it'll just be KSP, and then it'll be our two products. So Ba2 plus raised to the first power, since we have a coefficient of 1, times SO4 2 minus or sulfate, again raised to the first power. So that would be our answer for this question. All right, so calcium fluoride, the main component of the mineral fluorite, dissolves to a slight extent in water. Here we have our balanced chemical equation. It says calculate the KSP value for CaF2 if the calcium ion concentration has been found to be 2.3 times 10 to the negative 4th molar. So we are calculating KSP, which means I'm going to start out with our equilibrium expression. And I know all of my equilibrium expressions are products over reactants raised to the power of the coefficient. However, remember in these KSP solubility equilibria, we always have a solid as our reactant, and solids and liquids are not included. So all we have is our products, and we have the concentration of Ca2 plus raised to the first power times the concentration of F minus raised to the second power because I have a coefficient of 2. Now that I have that, I need to figure out what values get plugged in to my concentrations of products. Now you can probably tell from the coefficients of the balanced chemical equation that we're going to put that 2.3 times 10 to the negative 4th into the Ca2 plus, and then we're going to multiply that number by 2 for F minus because it has a coefficient of 2. But if that does not make sense to you right off the bat, you are free to do an ice table if that makes more sense for you personally. So we are starting with nothing. We're starting with our solid in water. So our initial concentration for our two ions are going to be 0. And since we're putting the solid into water and then the ions are being formed, the ions are going to have a positive X. So for Ca2 plus, that is going to be X. And for F minus, that's going to be 2X. So we can see at equilibrium, we're going to have X and we're going to have 2X, which is exactly what I said earlier. So in our KSP expression, we're going to plug in those values. So 2.3 times 10 to the negative 4th. And for F minus, it will be 4.6 times 10 to the negative 4th squared. So now plugging that in. we end up getting 4.9 times 10 to the negative 11th for our KSP value. All right, so now what happens when it asks you to calculate molar solubility? Because this is something that students do often get confused on. So molar solubility is the maximum amount of solute that can dissolve in a solvent to form a saturated solution at a specific temperature. And molar solubility is going to be presented in units of molar or moles per liter. So looking at this example, it says the KSP for the mineral barite is 1.1 times 10 to the negative 10th. Calculate the solubility of barium sulfate in pure water in moles per liter and in grams per liter. Now, since I'm not given an equation, let's go ahead and write one out. So I have barium sulfate, that's my solid, and then I have my double-headed arrow to show equilibrium. Then I have my first ion, Ba2+, that's going to be aqueous. And then I have my second ion, SO4 2-, that's also going to be aqueous. Now from here, the only value we're given to start this equation or this question is 1.1 times 10 to the negative 10th for KSP. So if I do an ice table to figure out what my values are for each of the ions in terms of X, I can plug that in to the KSP expression and solve for whatever X is. So let's start with the ice table. So we have R, which is reaction. We have I for initial. For our ions, those are going to start at 0. Then we have the change. We know these are going to increase by a factor of the coefficient, so this will just be X. And then I also want to just keep in mind, just because it kind of helps me understand the whole process, but in reality, the BaSO4 is also decreasing by a value of X because whatever I lose from BaSO4 is turned into ions. So I'm just going to put that even though I'm not actually including that into the ice table. And then finally, equilibrium. For equilibrium, I'm just going to have a value of X for Ba2+ and a value of X for SO4 2-. Now, if you can just see that looking at the balanced chemical equation, you don't have to do all of this in the rice table. But I just wanted to make sure that you understand where those are coming from in terms of the coefficients and the equation as a whole. So now that I have those values, I can go ahead and plug them into my KSP expression. So they're all a 1 coefficient. So my expression would be KSP equals my concentration of Ba2+ times my concentration of SO4 2-. Now, both of those values are X, so that means I know that my KSP is equal to X squared. And now I know my KSP value from my problem. So I can plug those into each other, so I know 1.1 times 10 to the negative 10th is equal to X squared. And now I can solve for X. And that gives me an X of 1.0 times 10 to the negative 5th. Now, because X is the same for all of the coefficients, because it's the same for my solid, and looking at the definition of molar solubility, it's the maximum amount that can dissolve. That means I can dissolve this amount of the salt into water, and that is my molar solubility, and it's already in concentration. So that is going to be my answer. When salts have the same cation to anion ratio, you can directly compare their KSP values to determine which is more soluble. So for example, if we're comparing AgI, AgBr, and AgCl, because they have the same ratio of cations and anion, we can compare their KSP values. So you can see AgCl has the highest KSP value, which means that AgCl out of these three is the most soluble. AgI has the lowest KSP, so out of these three options, AgI is going to be the least soluble. Same works with other cation ratios like PbI2 versus PbBr2 and PbCl2. With PbCl2 having the highest KSP value, that is going to be the most soluble comparatively. And then PbI2 is going to have the lowest KSP value, which means it's going to be the least soluble. And then you can go ahead and compare iodine versus chlorine in AgI and PbI2 and AgCl and PbCl2. And you can see that there is a correlation between the two. All right, so our final lesson of Unit 7 is on the common ion effect. Essentially, this is combining our last lesson on solubility equilibria with the lesson on Le Chatelier's principle. So what the common ion effect is essentially if we have a solution with ions already in solution before we dissolve our salt, what is that going to do to the equilibrium of the dissolution? All right, so you can pause and read the paragraph on the left, which is the technical explanation of the common ion effect, but I find it easier to just explain what it is. So let's say you were dissolving sodium fluoride into water and you are looking at the equilibrium of sodium fluoride with its constituent ions. What the common ion effect is saying is if I took NaF and instead of just putting it in water, I put it in salt water, meaning water that already had Na plus and Cl minus ions in it. Well, if I dissolved NaF into salt water, that means I would have an increase of sodium in my equilibrium, which means if I am increasing my product, I am going to shift back to the left, which is why it's saying that if you add a common ion, you're going to suppress your solubility, meaning you're going to go back into the solid and make less ions. So let's break down what's actually happening here. So a saturated solution is a solution that contains the maximum amount of a dissolved salt. If a second compound, which has an ion in common with the dissolved salt, is added to the saturated solution, the solubility of the salt is going to reduce and a solid precipitate will be formed. This is known as the common ion effect. So the solubility product can be used to predict whether a precipitate will form or not. And a precipitate will form if the product of the ion concentrations is greater than the solubility product, which is KSP. All right, so let's translate that to an example. So looking on the right here, we start with a saturated solution of silver chloride, which is AgCl. And at equilibrium, solid AgCl is in balance with Ag plus and Cl minus ions in solution. So that's this container here. Now remember, we know that AgCl has a very low solubility. It doesn't mean that if you saturate a solution, you won't have Ag plus and Cl minus ions in it. You'll just have very few compared to a very soluble salt. So again, we have at equilibrium, we have a saturated solution of Ag plus and Cl minus ions. Next, we are going to add in a potassium chloride solution. And potassium chloride completely dissociates and increases the concentration of chloride ions. So once we poured this solution of K plus and Cl minus into our beaker of AgCl, we are going to significantly increase the amount of chlorine. So let's just look at our equilibrium equation for AgCl. So when we add in that KCl solution, we are increasing Cl in this equilibrium. And by doing that, if I increase the concentration of a product, I'm going to shift towards the reactants. And in this case, the reactant is my solid AgCl. So by adding in that solution with excess numbers of Cl minus ions, I'm shifting my equilibrium back to the solid state, which is why AgCl is going to form when I add in that solution of KCl. And that is the common ion effect. If solid AgCl is placed in 1 liter of 0.55 molar NaCl, what mass of AgCl will dissolve? So we're given the KSP of AgCl. And remember, when we're given KSP and just a little bit of information, we're typically going to be doing an ice table. So let's start with that. So we have our solubility equilibria of AgCl. So we have AgCl as our solid. It is at equilibrium. So we're going to do double-headed arrow, Ag plus aqueous plus Cl minus aqueous. So notice everything is a 1-to-1 mole ratio, which makes things nice and easy. So let's think about conceptually what's happening here. We have a beaker filled with salt water, NaCl dissolved in water. Then we're going to put our solid AgCl in this salt water, and we're trying to figure out how much AgCl will actually dissolve. Well, if we can figure out how much Ag plus is in solution at equilibrium, then we can relate it a 1-to-1 mole ratio, and that's going to tell us how much AgCl we lost from the solid, which is how much is dissolved. So by taking that concentration and multiplying it by 1 liter, I have moles of HCl, and since I'm asked for mass of AgCl, I just multiply that by the molar mass. So let's start with our rice table. We have our reaction already. Now let's do our initial. For Ag+, at the very beginning when I put this AgCl into solution, there is no Ag+ in the water. So that's going to be a concentration of 0. Now, when I put that AgCl into that water that has sodium chloride dissolved in it, I do have Cl- already in solution. And since for every 1 mole of NaCl, I have 1 mole of Cl-, I can just use this value for Cl-. So I am starting with 0.55 molar of chloride ions in that solution from the very beginning. Now the change, of course, we're not really using the solid because it's not changing in equilibrium, but our products are increasing because we are dissolving the AgCl. So this is going to be plus X for the change and plus X for the change. So that's C. So then at equilibrium, I'm going to have X and I'm going to have 0.55 plus X. So now with that information and my KSP, I can go ahead and solve for my X. And once I have my X, that means I also have my amount of AgCl that was dissolved. So starting with KSP, remember the expression, KSP is equal to products over reactants raised to the power of the coefficient. But remember, our reactants are solid, so they're not included. So we're just doing the concentration of Ag+ times the concentration of Cl-. So KSP we are already given 1.8 times 10 to the negative 10th, and that is equal to X times 0.55 plus X. So in your calculator, because this is a quadratic equation, so you do have to solve it quadratically, you get X is equal to 3.27 times 10 to the negative 10th. Now that is telling me that this value is 3.27 times 10 to the negative 10th, which means when my AgCl was dissolved into this saltwater solution, I created 3.27 times 10 to the negative 10th molar Ag+, which means, since it's a 1-to-1 ratio, I also dissolved that amount from AgCl. So I can take that number, which is molarity concentration, 3.27 times 10 to the negative 10th. That's concentration, right? So moles over liters. And now I have liters, right? 1 liter. So I can multiply that by 1 liter. And it's the same in moles. So I have 3.27 times 10 to the negative 10th moles of AgCl. My question is asking for mass, so I have to do one more step, and I have to convert this into mass by multiplying by the molar mass. And that gives me, with the correct number of sig figs, which is 2, 4.7 times 10 to the negative 8th grams of AgCl dissolved. Now, one thing I want to talk about before moving on is this hard way of calculating. So I want you to go backwards and notice how small our x is. Now, because we know that AgCl has such a low K value, we know that x is going to be super small. So to make your life way easier, I would say it is safe if you want to get rid of this plus x and just leave it as 0.55 so that you have way less confusing math to do with a little bit less error. So if you did this instead as 1.8 times 10 to the negative 10th equals x times 0.55, you're going to get the same value for x because it's so small. So I wouldn't worry too much about that if you would rather just pop off that plus x to make your life a little bit easier, if you know that your KSP is super low and that x is going to be really small. Just a side note. All right, so calculate the solubility of silver chromate at 25 degrees Celsius in the presence of 0.005 molar potassium chromate solution. For comparison, the solubility of silver chromate in pure water is 1.3 times 10 to the negative 4th molar, and you are given the solubility equilibria and the constant. So remember, when we're just given the constant and only little bits of information, most likely we're going to be doing a rice table and solving for x. And since we are looking for the solubility of silver chromate, that means I'm looking for x that I get for silver and then relating that to Ag2CrO4. And that number is going to tell me how much of that dissolved or how much of that is soluble. And that answer is going to be in concentration. And that is what I'm looking for. So let's go ahead and get started. So remember, what we're doing is we're taking this silver chromate solid and we're dissolving it in a solution of K2CrO4. So we're already starting with CrO4 minus because that's in this solution that we're putting the Ag2CrO4 into. So we already have, since it's a 1-to-1, there's only one CrO4 minus in here, we know we're starting with a concentration of 0.005 molar. And then we're starting with 0 Ag plus. So because stoichiometrically we have a 2, it's going to be plus 2x. It's going to be plus x. So at equilibrium, we're going to have 2x, and we're going to have 0.005 plus x. So now doing our KSP expression, we know that KSP is equal to the concentration of our products, Ag plus raised to the power of the coefficient. And we're not putting a reactant on the bottom because it's a solid and we don't include solids. So now we can plug in those values, and I already know KSP. So 9 times 10 to the negative 12 equals, I have 2x squared times 0.005 plus x. Now I'm technically doing this the correct way. If you would like to remember, take this off to make your life way easier in terms of solving, I am okay with that. Again, just because this KSP value is so low, which means this X value is going to be really, really small. So it's not really going to affect the math much. So if you'd like to do that for ease, you can definitely do that. So let's go ahead and plug this into our calculator to get X. And I get 2.12 times 10 to the negative fifth for my X value. So as you can see, if I got that here, it really wouldn't do much for that value in total. So now that I got that for X, and I know that I lost 1X for this equation because it has a coefficient of 1, I know that that X is my solubility of silver chromate. And then to verify that you understand what's happening here is if I were to take silver chromate and put it into a solution that already has chromate from the common ion effect, I should assume that silver chromate would be less soluble because that CrO42 minus is pushing the equilibrium left. And that does check out because for comparison, we were given the solubility of silver chromate in water, and it is greater or more soluble in water, which checks out with the common ion effect.